So I'm assuming you can hear me and you can see my my PowerPoint that says chapter 3. Is that correct?
Yes.
Anybody?
Yes, Professor.
Yeah.
Okay, thank you. Thank you very much. Okay, good afternoon, everyone. We covered all that, and then we just had 2 examples to finish, so we can wrap up the this chapter. So we did all these. 3.1 we did, 3.2 we did. So we're gonna do 3.3. Before I begin, any questions from last night from the lecture? Any question? Any comments? All right. So we're gonna do 3.3. So again, it says determine the ACI design flexural strength. That means the moment capacity of the beam. Exactly the same as 3.1, 3.2. Different, of course, different beam with different rebars. Okay. So he's asking us find the flexural strength, meaning the when it says design, that means MU or phi MN, same thing, the ultimate. So there's our section. B is 12, D is 15, H is 18, AS is 4.68. So first thing we do is we check the steel percentages, rho, so we can compare it against rho minimum and rho maximum. So rho, we said it many times, is defined as the area of steel divided by B times D. So meaning that how much steel do I have with respect to the cross-section of the concrete? Okay, what is the ratio of the area of steel with respect to the cross-section of the concrete? The only thing is we really should be doing 12 by 18, but for beam we only do 12 by 15, so B times D. We ignore this small piece of concrete below or from center line to the bottom. When we do slabs, we're gonna take the entire thickness of the slab because the slab is not that thick. It's like 6 inches, 8 inches and all that. So there you go, rho equal AS over BD. AS is 4.68 from here, and then B is 12 and D is 15 from here. B is 12 and D is 15. So we know that our actual rho is 0.026. So in plain English, this is like 2.6%, right? If you multiply by 100, is 2.6%, which really mean in plain English, if I take this cross section, 2.6% of it is steel. The remaining 97.8% is concrete. That's really what it means. Now I have to, this is my actual rho, meaning that this is what I have in the beam. Now the thing is, did I violate anything from the code requirements? And how do we check that? What is rho minimum that the code tells me I have to use? Rho minimum, like we said last time, either check the equation or go to table A7 and you will find rho minimum. All you need to know is F prime C is 4,000, Fy is 60,000, okay? Then you can find rho minimum. You know, in that table, you can find rho min, comes out to be 0.003. If you plug this into the equations, and let me go back there if you don't mind. If you plug those into the equations, you're going to get the same answer right here. Remember this equation, AS minimum, which leads us to rho minimum? Same thing. But why do this when you can just pick it up from the table? All right. So rho minimum is this. Look at our rho, 0.02, rho minimum 0.003. So we meet the rho minimum, no problem. And then again, why does the code ask for rho minimum? Rho minimum, that means I have minimum area of steel because AS minimum is rho minimum times B times D. See right here, look, if you cross multiply, AS equal rho BD. So if I'm using rho minimum, that means I have AS minimum. AS minimum is rho minimum B times D. Why does the code ask for that? Just to make sure we have enough temperature and shrinkage steel that the member is not gonna crack and then that the member carries its own weight without cracking. Okay, that's what the rho minimum is. Rho maximum, we should be below rho max, right? So look at our rho, 0.02. Look at our rho max, 0.018. We exceeded rho max. See that? We exceeded rho max, so this should raise a flag. But from here, we cannot tell whether it's good or bad yet. You will see, but it should raise a flag. So it says here, therefore, epsilon T, the strain in the steel is less than 0.05. Remember that? Because we want that rho to be over 0.05. That means the steel is going to yield. We are less than rho minimum maximum, but this one, it's not. So, but we'll see what happens in a second. Step B is compute A, ASFY over 0.85 F prime C times B, just like the previous examples. We have everything here, 6.88. Beta 1 equal 0.85. Y for F prime C less than or equal to 4,000, always 0.85. Same as example 3.1, 3.2. C is equal to A over beta 1 or A equal beta 1C. So you have A and beta 1, you can find C. And please do those examples on your own when you review and do them right, in this weekend. Because those are very easy and very important to continue going, okay? What is the strain in the steel? Is D minus T over C times 0.03. We already derived that in the examples, and we derived it from the similar triangles when we did these problems. Remember that? We did that. We derived those. So now you just have to use it. So from here, I know everything. I know D and C and C. C is 8.9 and C is that. D, what is D? Look at the figure. D is 15 inches from the top to the center line of the bar. So then that epsilon T gives me 0.00256. Okay? So 0.0256. Let's see where that puts us on the chart. 1 second. So let's go back to this chart. Right here. See, this is the epsilon T, the x-axis. 0.0026, somewhere here. It's less than 0.004. What did we say in this area? The code does not allow us to be in this area. So this beam is no good, right? This beam is no good. We said we have to be above 0.005. If it is above, then phi is 0.9. We can be in this area greater than 0.004, between 004 and 05. It's acceptable to the code, but phi is no longer 0.9, it's less than 0.9. So we said if this is the value, you go up until you hit this solid line, then you go horizontally, you read the curve, or plug your epsilon T here, and then you can find the value of phi. All right, so we are 0.0026 somewhere here, the beam is no good. That's why these examples are good. It makes this graph sync. All right, so 0.00256 less than 0.004 from the graph. Therefore, section is not ductile and may not be used per ACI. You cannot use that. So somebody could say, then what? What happened? You have to change this section. You have to change the dimensions of it. Okay? Because look what happened. If you make it bigger, B is bigger and D is bigger, right? So look what happened to that. If you make B and D bigger, what happened to the rho? It goes down. It goes smaller. So then you're going to be less than rho max. So then and then when you do that, then when you calculate here, then you might be below that number. So that means you have to refine your design to use this beam in your building. All right? 3.4. You notice every one of those examples is a different row, different value to illustrate what you can and can't do in the table, in the graph. 3.4, same thing, designed AC, designed flexure strength, 4,000, 60,000. The only thing is we have a different beam. See, B is 10, D is 15, H is 18, AS is 3. So what is the design moment capacity for this? Same thing. First, we check the steel percentage, AS over BD. AS is 3 inches square, over B is 15, and D is 10, and 15 is D, 0.02. Rho minimum, again, 0.03. Why? Because look, we're using the same F prime C and Fy. So that's not going to change. And most of the time, that's going to be the case. In real life, in the course, all it's going to be the same, 0.03 from this table. Rho is what? Look at that. Rho max is 0.0181. This is larger. Again, it raises a flag. It's not necessarily, you cannot be used, but it raises a flag. In the last example, it raised the flag. We couldn't use the beam. In this example, it raised the flag. But can we still use the beam? We'll see. We'll see in a second. Therefore, not tension control. That means it's not over 0.005. We're not going to be in that area. All right. So go through the same process. A equal to this. We go a little faster now. 5.29. Beta 1, again, 0.85 because for 4,000 PSI concrete. CA equal A over beta 1. Epsilon T is that. You plug in the numbers, look what epsilon T is, 0.00423. See that? So let's go to the graph, 0.00423. That's the strain in the steel. Look here, 0.0423, we're here. We're here. Can I use this beam? Yes. It's between 004 and 005. The code said I can use that. The only thing that my phi is not 0.9. I'm going to put 0.0423 somewhere here, go up, and then go horizontal, or put the epsilon T 0.00423 here and solve for phi. And that's what he's going to do. Look at this equation and remember that. He's going to use this equation to calculate phi. Remember, all you all have to do is epsilon T here. Look at the 250 and the 3 and this 0.65. This equation is different than that. See that? This is 150 over 3. This is 250. This is 0.75. This is 0.65. So this is the one we're going to use, right? Because the other one is for spirals. That's not a spiral we have. All right. So 0.0423 between 0.004 and 0.005. Look at this, 0.00423 greater than 0.004, okay, and less than 0.005. Therefore, the beam is in the transition zone between those two. It's okay to be into the transition zone. The only thing about the transition zone, we said the beam is not economical. It's not the best design you have. If you're designing from new, then you would go back and change the dimensions of the beam to make sure you're out of that zone. But if you're doing an analysis of an existing building, you cannot change the design. So if you prove you're in that zone, you're okay. Okay? If somebody is asking you, prove that this beam is good, yeah, it's in the transition zone, is okay, but you would not design it like that. From scratch, you would change the design.
Professor?
Yes.
What would happen if you do review, you're checking the beam and then it's not in that zone? Like what would you do? Or what would happen?
Then the good question. Then that beam is not good. It's not good. Then what you have to do, you have to look into retrofit. How do you retrofit that? Right? To make it stronger. And there's many ways to do that. One way is these days what they're doing is they're wrapping it up with carbon fiber sheets or e-glass sheets. What they do is they I don't know if you know what that is. It's like a cloth made out of fiber, and what they do, they put resin on it like a glue, and they attach it to the sides of the beam, the bottom of the beam, and the other side, and that gives it more tensile moment capacity. So that's one way. Another way is they put a steel jacket to it. Of course, that's doable, but the other one is easier. So you have to retrofit it if the city or the government agency asks you to do that. In theory, the beam is deficient, right?
Mm-hmm.
And then it could be deficient by today's code, by the way, but it could be, it was built in the 1960s, and at that time it met the code. So that could be the case too, and the city can say, you know what, we're going to grandfather you in. You don't have to retrofit that. So there's a lot of things. It depends on the government governing agents. Does that make sense?
That makes sense. Thank you for
All right. You're welcome. But good question. All right. So now we go ahead and remember, he's asking you for the moment. What is the design moment? Design moment is phi mn. Okay. So what is mn? Is ASFYD minus A over 2. We have all these numbers.
Pardon me, Professor.
Yes.
Yes, just out of curiosity, is this PowerPoint at all going to be on Beachport for us to access for future reference?
No, remember the PowerPoint, I said this is really, what do you call that? It's protected by law. I cannot post it, unfortunately. You know, it's copyright protected. But whatever I do is, if it's mine, I post it, no problem. But like the one for the project and the lab, those are mine. I posted those, but this is not mine. That's why. Yeah, I'm sorry about that. I wish I could. So this question comes all the time.
Very good, sir.
You're welcome. But all these are coming straight from the book. Very, very closely tracking the book, really. AS is 3 inches square, FY is 60, given D is 15, A is 5.29, we calculated, so it comes out to this, divided by 12 comes out to that. Now phi, remember, is not 0.9 because if it was, if this value was 0.005 or more, then phi is 0.9. But it's not, so we said we have to calculate phi. So how do we calculate phi right here? Phi from figure 3.5, the one I just showed you. There's the equation, remember, 0.65, there's the 250 over 3. The other equation for spiral, this was 0.75, this was 150. So look at our phi, it comes out to be 0.836. And if you do it graphically, it's gonna be that number or very close to it. So then phi mn this is mn is 185. I multiplied by 0.836 is equal to that. So look at this, 154, right? 154. And then what did we do? 185 is 100%. I am taking 83.6% of that. So I'm reducing it by like 17%, right? If it was phi equal 0.9, then I would only reduce it by 10%. See that? So I'm reducing the moment capacity by 17% because it's not ideal. We want it to be in the zone where the steel is gonna sag so people can run out. So that's why. But the code is allowing us to do that. Is that clear? So this is that, and this finishes that chapter. So please review the chapter. And then this weekend, I'm going to assign homeworks for you from this chapter and maybe from the cracking moment. So for sure, look for that. And I wanted to finish this because next week, I'm going to start the beam design. We're going to start designing the beams. All these, as you can see, the examples, the beams are given. The dimensions are given. The steel is given. It doesn't talk anything about loads. Those are analysis problems. Okay? Next chapter, we're not going to be given these beams, the dimensions, not the steel. All they're going to give us is the loads. Remember, this is dimensions given, steel given, how much moment can it carry. In the design, they're going to give us the loads, dead load, live load. From those loads, we're going to calculate the moment, and then we're going to proportion a beam like this to carry that moment. See that? That's going to be interesting. So that's going to be the design of beams. And then once we finish that, and then right after in the same chapter, we're gonna design the slab. You know, we know how thick the beam and the slab needs to be roughly. Now, next chapter, we're gonna final design those, and then after that, we go back to the project, and then you can design your beams and slabs and put the rebars in. See how we're tracking? We're doing in a very systematic way, so we can follow up with the design project. All right. Any question on that? All right. Thank you. This is for that. So I'm gonna switch now to the lab portion. Again, not much, but we will finish that. Let's see, lab section. Okay, so if you remember lab assignment 1, we finished. Lab assignment 2, we did part 1 and part 2, and I hope you've done it for your group and put it into your 3-ring binder by now. With part 3 for the shear reinforcement, we're gonna wait until chapter 8. But now I wanna go to assignment number 3, lab assignment number 3. See how everything is flowing? We're working on all the stuff, the lecture, the project, and the lab. So we're doing it together so we can finish everything by the end of the semester. All right. So let me new share here. Okay, now I hope you can see my screen, and we're gonna go to the assignment number 3. So today, this one here is, we're gonna talk about as if we were in the lab, and if we were in the lab tonight, we would be mixing concrete. We would be mixing concrete and then put the concrete in the beam, in the form that we talked about last time, and then we put the concrete in the cylinders that we talked about. So that's what we're gonna do tonight, to cover those steps, and then I'll show you part of the presentation and all that. Okay, it says you will need to buy 200-pound Quikrete. Those are the yellow bags that I showed you, and I'll show you again tonight. Each bag weighs 90 pounds. And then remember how we estimated how many bags we need? So we would have the bags ready, and they are ready in the lab. The concrete mix with a 4,000 PSI concrete strength. So on the bag, it says 4,000 PSI, because that's what we wanted. We wanted to buy that. Follow instruction given below. It's a typo here. Below is misspelled. To make your concrete mix. So how are we going to do that? If we were in the lab, you would have this page with you and follow the instructions, okay? It says after making the concrete mix, rinse off the mixer and any tools you have used. Just to keep everything clean for the next class, next groups and all that. And because, if you don't wash the concrete off, it's going to get hard and you cannot wash it anymore, it's bad. Even these instructions are given on the job site. You should wash all the shovels and then the equipments so they can be reused later. So how do we going to mix? What is the mixing instructions? It says, pour water into the mixer. You will see the picture of it in a minute. It's a red mixer. I showed it to you at the beginning. And we're going to pour water in the mixer first. How much water? It says use 0.1 pound of water to each pound of Quikrete. So 90 pounds of Quikrete is going to take 9 pounds of water. I remember we brought the scale from the materials lab, and the students measured 9 pounds of water and put it in there in the mixer. Turn on the mixer and keep all hands off the turning blades. Safety. And then add Quikrete. You start slowly adding Quikrete mix into the mixer as it's mixing. Okay? So this is a very sensitive operation. You have to be careful with it and make sure hands off and all that stuff. You're going to let the mixer mix for about 3 minutes. And you will visually inspect the mix. If it needs a little bit more, you let it mix some more. See, more if needed. Sometimes dry mix gets stuck to the walls of the mixer. If that happens, stop the machine and scrape the concrete off the walls, restart the mixer and mix until the concrete paste is homogeneous. That means the paste is homogeneous, looks like a little fluidy, and you know how concrete looks like. Okay? Now, if needed, add more water, but not more than 0.01 pound per each pound of Quikrete. See? And most of the time when we mixed, the mix was really dry. So we had to add more water to it. But we added a little bit at a time and not to exceed 0.01 pound per each pound of Quikrete. And we kept the amount of water we added, we kept track of that. Okay? We kept track of it so you can report it in your report. After you are done with mixing, tilt the mixer and pour the concrete into the bucket. So when we're done, the mixer can be tilted to its side and you empty into a bucket. And then pour the concrete from the bucket into the formwork. Then we can use the spatulas and all that to take it from the bucket into the cylinders as well as the concrete form, the beam form. Okay, that's what we would have done. Now, how do we place the concrete? Concrete placement says prior to concrete placement, mark position of the chairs on the interior of the formwork. Remember we talked about we're going to have a cage, a steel cage in there. That cage is going to go inside the wood form. But we don't want that cage to touch the bottom of the form because we want concrete to go underneath. So we use something called chairs. They are plastic small pieces. He's saying just mark where you want to put those chairs before you pour the concrete. And usually at both ends, maybe 6 inches from each side. And maybe one in the middle, it depends. But 2, 1 each side should be enough. All right. Remove the rebar cage, the forms from the forms, and saturate the inside with that. We didn't do that really. What we did really, because he said spray the forms with a release agent. It's a chemical compound liquid that you spray the form with, so the concrete doesn't get stuck to the wood. But what we did is you just spray it with water. That's good enough. But on big jobs, professional jobs, usually they spray that so the form don't stick to the concrete. And we didn't take out the cage from outside. We left the cage in and we poured around that. You can do it either way, as long as the concrete goes under the cage. Okay? It says here with the bottom U-shaped portion of the formwork braces in position, start placing concrete 1 inch at a time. Okay? So you start placing 1 inch at a time, and then you tap it with a steel rod so that no voids in there. So in bottom line, you start putting the concrete in carefully. Position the chairs and put the rebars cage in place. See, our cage is already in his case, they took the cage out, put 1 inch of concrete, and then brought the cage back. The problem with doing what he's doing is that you have to take that top piece, and I'll show you in pictures in a second, the top piece of the form out, then you have to screw it back on. But again, I'll explain that again when we go to the pictures. Pour the concrete and penetrate it with rods to release the air pockets. So you tap it into with that. After you fill the formwork with concrete, place the handles and smooth the top. So you smooth the top and place that top sheet. We call it the handle, and I'll show you, which is part of the form. Place the piece of plastic sheeting flush against the top of the surface. So what we do is we smooth the surface out and we place a sheet of plastic on top so the moisture in the concrete doesn't evaporate, because we want every drop of water to stay for the process of hydration that's gonna happen inside the concrete. You covered that in the materials lab. And then at attach the top 1.2 to complete the form. That's that top piece of wood 1.2 to finish the form. But we didn't do that, and I'll show you why. Well, because we always left it on. Cure the concrete by spraying it with water every 24 hours for 3 days. So in theory, you're supposed to go by and spray water on top for 3 days. it's better for the concrete. It's good to keep it moist. And in fact, if you do that and you listen to it, you're gonna hear it fizzles. You're gonna hear it fizzles. It's soaking the water, and then you're gonna feel that it's releasing heat. Just part of the material characteristic. So with that, then you fill the cylinders. Remember, we have 2 cylinders in there. Make 2 6x12 cylinders by filling the molds in thirds: 1/3, 2/3, 3/3. And as you're doing that, you're tapping it with the steel rod. You've done that in the materials lab also. And then tap it 15 to 20 times or as needed. And then mark cylinders indicating your group. Then you mark on the outside which group number you are in, smooth the surface out, and then put the white cover on it, right? And then you set it next to your beam, and you mark your beam and all that. Rinse all the tools off that you use so they can be used by the next group, okay? So this is what we would have done tonight if we were in the lab. We poured the concrete beam, covered it with plastic, took it outside in the parking lot, put it in the corner, and put those 2 cylinders, smooth the surface, cover them with the white lid, and mark them and put them outside. And the reason we do 2 cylinders is when we test them, if they're both good, and I'll talk about that when we cover them in the machine, then we take the average. If one is bad, we at least will still have 1 good. And what is the reason for the cylinders? We want to determine the actual F prime C. The bag told us is 4,000 PSI, but the actual F prime C is what you get tested in the lab. At what pressure is going to break. That's your actual F prime C. All right? So we'll talk more about that. All right, so we did that. And that's it for assignment number 3. Any question on that? Any question? So no action item for you to do at this time except when you write your lab report, you're going to write about this. And you can copy and paste it. I don't mind. You can use your own language. You can copy and paste. You can modify. But this has to be part of your lab. Assuming you went to the lab, how did you mix the concrete? How did you place the concrete? How did you do your beam and your cylinders? Okay? Everything is written for you, so you're welcome to copy and paste it or do in your own language. Any question on that? All right. So we're done with the assignment number 3. Let's look at assignment number 4. See what assignment number 4 say. And that's the last assignment for the lab. Okay, so let's do a new share. So again, assignment number 4. Let's say now we poured the beam and the cylinders, and we waited 28 days minimum. Of course, we would have not hit 28 days exactly, as long as it's after that, because the way the class is scheduled. So after 28 days, we will go to the lab and do what? Test the beams and the cylinders. Okay, and that's what assignment number 4 is: testing of beams and cylinders. And then I'm gonna go to the PowerPoint to show you that instead of just reading here. But then again, so it's okay. That's what that is. I'll come back to this in a second, but let me go to the presentation. So I'll show you what we would have done in there. All right, let's see. Sorry, just give me a minute here. What's going on here? Let's go fall. Class project, no. Spring. Lab, okay. Where is that? Lab folder and videos. Sorry guys, just give me a second. Spring. Let's go to the phone. Okay, got it. Okay, let's do a new share. So I'm gonna go to this PowerPoint, and you have that. You should have that posted, okay? And then as a reminder, guys, remember I posted that video. That video, I made that video and I spoke in it. So please watch it again after tonight. Kind of that kind of, go all the way through it, okay? So we went through this here. You remember we were saying, this is the 1x2 he was talking about, the top piece. The way he was thinking is that, leave this piece off, put your cage in, and then after you pour it, then put that back. We didn't do it this way because I was worried about the pressure of the concrete inside. It's going to open the form. I needed that bracing at the top. So that's the one he was talking about. See, you can see it here. What we did is we had the cage in first and then put those on top, and we poured around the steel. No problem with that. We'll see it again in a second. We did all those. So these are the ones. Please make sure you are doing those as you go. Okay? Make sure you finish those, put them in your ring binder. Remember, we did the pre-test calculation. You also should have done that in your group. Just as a reminder, we did this pre-test assuming F prime C is 4,000. We're going to do the same calculation at the end. Once we know what is our real F prime C when we crush those cylinders, then F prime C is going to be around maybe 3,000, 2,800. We're going to do the same calculation with a different F prime C. We're going to call that post-test calculations. Okay? So we did all those. We didn't do the shear. We skipped this because of like I said, we have to wait. And then we calculated P's and all that. All right. So what I want to start is here tonight. So these are the rebars that we used. We took those bars and we made them into a cage. Right? We would have done that before you poured the concrete. And then we put the cage inside. See how we put the cage, then we put this piece on top? So that's what we were talking about. We always had this here because I wanted to brace the sides so they don't, because the pressure of the concrete is a lot. So I didn't want to risk losing the form, because think about this. This form is attached to the bottom only with some small screws from the bottom. And look how thick the wood is. It's not that strong. And then just another comment here is, look at these, we call those stirrups. They are deformed bars. Usually even in real life, those stirrups are made out of smooth bars. Okay? But here I remember this case because the company did not have any smooth bars, though they gave us these concretes, these deformed ones. And they donated the material to us, so we couldn't be too picky about that. So that's the cage. And then look at these thin wires. That's what you had to tie the stirrups to these bars using these wires right here. Okay? So this is a blown up picture of it. You can see that. Again, when we calculate how many stirrups we need, you will see everybody is going to come up with an answer. We're going to need one every 2.5 inches. A lot of them. And you will see why later on when we cover that chapter. So there's the yellow bag we were talking about. Quikrete, 90 pounds each. So this is the one. And there's the cylinders. 2 cylinders, 6 by 12. These are the white covers to them. In Europe, by the way, they do not use cylinders. They use cubes. They make concrete cubes and crush those to find their F prime C. Okay, so just different codes, different system. So remember this, we calculated how much concrete you need, and based on this, you determine how many bags we need. We already did that. There's the mixer we were talking about, the red mixer. Concrete mixer, see how it stands? It has 2 wheels, has a handle. You can lift this handle and move it around. Okay, and then it has a electric wire in the back. You can plug it in, and that's where you get the power for it to rotate. These are the blades that he said, make sure you clean the blades so no concrete is stuck to it. But you have to be careful around this machine, okay? Anything that moves, as you know, you have to be careful around. So you remember we put 9 pounds of water, then we start adding the bag concrete. Of course, one guy couldn't carry the bag, so 2 or 3 guys had to carry it and slowly dump into a little bit at a time while the mixer was going. You know, honestly, it doesn't make sense. To be safe, I would put the bag in, then add the water to it. It's not going to make a big difference, okay? So, of course, in real life, we don't use these mixers anymore. It's already mixed that goes to the job site. They use these mixers when they doing masonry, when they are doing masonry work, because they don't need a lot of concrete for that. Like, you know, when they do the masonry work, they mix sand and cement, and they usually mix it with that. And then after it's mixed, remember, they dump it into this bucket. And this is a 5-gallon bucket. They dump it there. And from there, using the spatulas and all that, then they put concrete in the beam, and they put concrete in the cylinders, and they tap them with this rod. See this rod? And this is finished beam, and once they do it, and they tap it, and then they smooth the top of it. See, unfortunately, you missed doing that. Blame COVID for it.
Professor?
So that's what we're talking about, okay? More pictures. This is the tapping, the wire tapping, the rod tapping. Remember, we put this in third, 1/3, 1/3, 1/3. So we don't have voids in there, and we tap it with this 15 to 20 times. We smooth the top, and then we cover it right here. See, the top is smooth, and we put the white lid on it. And there's the beam. There's the spatula we use to take the concrete from the bucket to the here and there. And then those 2 hammers, the students used to tap on the sides carefully, as if you're vibrating the mix, so it can seep into the down, so no voids in there. All right, so this is what that is. Smooth the top, cover it with a piece of plastic, and move it out to the parking lot. And then mark the cylinders and put those next to yours, and then that's your beam and then cylinders, and they would have to cure for 28 days. Any questions so far? So I hope you're getting the feeling as if you're in the lab. I know it's not exactly the same, but I didn't want you to miss anything, what was done there. And then the video also discusses the same stuff, and you can also hear it one more time. Please do that.
The mixed, quick question, Professor.
Yes.
Are those for the mixing machine that you just showed a couple slides in that?
Yeah, the mixer, yes.
This is the same as the one that gets carried around by big trucks or big cars, right?
No, this is on a smaller scale. They come different sizes. But the same idea.
The same idea. Okay.
Same idea, but when you have the truck, you're not talking about the ready mix truck that does this, right?
Yeah, I'm talking about that one.
Yeah, that ready mix truck, the
Yeah.
concrete is already mixed inside.
Oh, okay.
All the concrete truck does is they have a chute. They attach a chute to the end,
Uh-huh.
and then they have two ways. If let's say you're pouring a footing below ground, then the chute is put on, and by gravity, the concrete will flow down. But if you are pouring a slab, what they do is that ready mix truck dumps into a big pump, and then the pump pumps it up to that. So if gravity doesn't do it, then you have to pump it. Does that make sense? Yeah. So you will never see this on a ready mix truck. No, you will see this on a contractor's truck, on the back of a contractor truck who is going to do maybe small job, and then he only need to mix 1 or 2 bags.
Got it.
But if you need a lot, then you usually get ready mix.
Professor,
All right. Any other questions?
if it's already mixed, then what is the machine doing for the ones on the truck?
Yeah.
No, usually if the contractor has this machine on his truck, he's not getting a ready mix.
No,
You
the
see
big
that?
ones, the big ones on the trucks.
Yes.
So if the concrete is already mixed, what is
Yes.
the machine doing to the concrete?
This machine, the red machine,
No, the big one on the trucks.
or the big one. Okay, the big one. If you notice, although the truck is there, you will notice it rotates very slowly. Very slowly. So why? So the concrete doesn't get stuck to the sides, or it doesn't get dry.
Oh, that
Now,
makes sense.
once they get to the job site, then they put it on a higher speed and mix it more. Now, the only thing as an engineer there, you need to be careful and don't let the driver add more water to it, because there is a hose, a spray hose. They can spray water into there. Okay, since you asked, we can go into in some depth here.
Mm-hmm.
It's okay to spray some water if you think it's a hot day and then some evaporation took place. Yeah, you can spray some, but by code, the concrete truck cannot come too early to the job site. They cannot stay, I believe, more than 1 hour waiting for you to get ready. If they come early and you're not ready and they have to wait exaggerated 3 hours, the concrete is no longer good. See? Usually the job specification will tell you, depends on the project, how much the concrete truck can wait before emptying the product. Because the longer he waits, the worse it is. Why? Because in that time, what's happening to the concrete? The process of hydration is taking place, and you don't want that to happen too much, because really the concrete is getting cured in the truck before it gets to the forms, and we don't want that. So you have to be careful. Sometimes some drivers messes up and he gets stuck in traffic or something. He comes out late, and in order to do it, he starts spraying water and mix it again. It makes the concrete bad. If that happens, you have the right as an engineer to reject the truck. Tell him, I don't want the truck.
Wow.
I don't want that. Then he takes it back and then bring you a new load. And it's not a big deal, really. It's not a big deal to the company. So this is like a quality control matters. Hopefully you will be aware of that later. Any other questions?
Wow, everything is
All
so
right.
calculated down to like the truck times and everything. That's
Absolutely.
interesting.
Absolutely. This is called QC, quality control. Because remember, if we're calling for 4,000 PSI, it better be 4,000 PSI. And how are you going to get that number? By doing everything right. If you are pouring a bridge slab and counting for 4,000 and the engineer designed 4,000, you cannot put a 3,000 PSI concrete. The bridge is not going to survive. So that's why our jobs, like I said it before, it comes with high liability. We have to be very careful with that.
Yeah.
And that's why there's a lot of specifications, there's a lot of requirements, and that's why we have inspectors on the job. The inspectors make sure what delivers to the job is what the engineer specified.
I see.
right.
That makes sense. Thank you.
Okay, you're welcome. Any other question? All right. So continue. Then this is what we said we do. And then now, after 28 days, what happened? We stuff into the to break them. This is the machine we said we're gonna place the beam on to break it, and you'll see a better pictures. This jack, hydraulic jack, is connected to that machine, and it's pumped by hand. See that? This lever arm. One student would pump that. One student would read the gauge here. The gauge gives you a PSI reading. That's a pressure. And then you will see in a little bit when. And let me jump to that. I'll come back here. This is how we equip the beam. We also equip this gauge here is attached to the center of the beam. Its function is as the beam is deflecting under the load, this gauge is reading the amount of deflection. So one student would man this, reading this dial. One student is pumping by hand, and the other student is reading the pressure gauge. That's how it was done as a team. All right? So we'll come back to that in a second. All right, so this is the machine. And then this is the, you've seen this in the materials lab where you put the cylinder and you crushed it. This machine is connected to this computer, and this computer is gonna display a stress strain curve for you. All right? You've seen that.
Mm-hmm.
So again, this is blown up of that. There's the machine. There's the this. So, and again, this machine is gonna pump pressure into this jack that's gonna push down on the beam. The only thing that this pressure is gonna be in PSI. And remember when we calculated the force P is gonna take to crush the beam? Well, this is a PSI. We have to convert that into a force. And then we'll talk about that later in the presentation. I'll show you how to do that. All right? So this is the setup here. So there's the cylinder being positioned to be tested. Notice that has to be centered with the machine. This top of this swivels, meaning it goes like this. Why does it swivel? Because we wanted to take the shape of the top of the cylinders to minimize eccentricity. And also in the real lab, what we do, we put a piece of rubber pad on top of that. It's about 1/2 inch thick. So between this and the rubber pad, then it minimizes eccentricity. All right? And then you break the cylinder, and we'll see a picture of the broken one later. And then this is how you position the beam. See, beam ready for testing. You set it up here. Make sure this distance is equal to that. That means the beam is centered. And look at the center. We put a line in the center of the machine. Make sure it's centered with the beam. We measure the beam, divide it by 1/2, and we draw a line. You cannot see it here. And then we make sure the two lines lines up. Okay? So we make sure the load is in the center of the beam. Why is that? So the equation moment equal PL/4, because that's the formula when the force is in the center of the beam. So you try to do as much accurate as possible. There's the broken cylinders. So look at this. This cylinder broke. Look at the crack. This is a perfect break from top to bottom, meaning the eccentricity. You know the eccentricity, what that is, right?
Mm-hmm.
If the force has to go through the centroid, if it is off the centroid, that distance, we call it eccentricity E. You've seen it in your geotechnical, right? So this is a good break. This is a good break. Look at this. The entire cylinder broke also. Sometimes the cylinder would, if it's not the level at the top and bottom, it would chipped off. It would get chipped like this. That's not a good break. You have to throw that out. The machine will stop because to the machine, let's say the cylinder is broke, but that's not a good reading. That's why we make more than one cylinder. On real jobs, they make about 30 or 40 cylinders, not only one or two. They make 30 or 40 of them, and they wait a few days and then they take them to the lab. Because why? Because they start breaking them at 7 days, 14 days, 21 days, and 28 days, because they see how the trend is going. Are they moving toward the ultimate or not? So that's what they do. Okay, so they do a lot of cylinders. When you're on the job, when you're working there, you will see a lot of that. So, yes, question?
Just for information, I know the cylinders are very in a small size. So what about enlarged size that they have to make? So do they make more than one for those two? I mean, more than 2, 3? If they
Yeah, of course. Like I said, on large jobs, they make like 30 or 40 of them. 30 or 40, because some of them might go bad. Some of them they test at 7 days, some of them at 14, and some of them they test like at 14 days, because usually they start removing the forms at 14 days. But they cannot remove the forms before the F prime C reaches certain amount. And how they going to know what it is? By crushing the cylinders. Does that make sense? So they can move the cylinder, the form, and go take it somewhere else, and then reuse that. Any question? All right. Very good. And then, of course, when we measure this, we're going to compare it to the 4,000, right? The 4,000 was the goal, but we didn't get that. In our labs, we did not come close to it. Ours were at like 2,500, 2,300. I think one group one time only got 3,000. Okay, but nowhere close 4,000. Because you're going to get this if you do everything right. That's what the ready mix does. Mixing by hand, you're going to be below that. So that's what this is. And then the machine is going to, for the cylinders, right? Remember, concrete cylinder, stress strain diagram is going to look like this. So look at this. The x-axis is strain. The y-axis is stress. So if you look at the top and you go horizontal, let's say it's 2250. It's higher than that. So it's around 2300. Okay, that's the reading for this specific cylinder. For every group, I'm going to give you those numbers later on, so you can do your post-calculation based on that later. And then the test results, look at this. So we had 2 cylinders, 1 and 2. The high diameter and F prime C, we estimated the same, right? No change. But look at the measured. The 12 still measures 12, the 612, because the cylinder doesn't change. But look at the F prime C, 2340. 2340, so this, from here, if you read it, is 2340. It's over 2250. So look at that. We shot for 4,000. We measured 2340. So this is your actual F prime C. When you do your post calculation, this is the F prime C you're going to use. And that's what's going to give you how strong is your beam based on that. The first calculations we did, we assume it's going to be 4,000, but it didn't come close to that. And no problem. It's a class, it's a lab. It is what it is. Now, I put question mark here because this number should be different than that, because there's no way you get the first cylinder this and the second cylinder that. There's no way.
Yeah.
Okay.
So this would be considered as a failure if it was a real job, right? For a real job.
Yes, absolutely. This is a big failure on a real job. Somebody is in trouble. Can you imagine somebody poured a bridge deck and then this is the actual results? That bridge deck is coming down. Who's going to pay for that? You know who's going to pay? The ready mix company.
Okay. So when you do this, so let's say you want your estimate to be 4,000. What about if it was like 3,900? Or
sometimes there's a tolerance there, just like everything else. There's a tolerance that the code allows you to do that. If you are within that tolerance, it's fine.
Okay.
But if you're not, then not the contractor, not the engineer, not the owner, the company that delivered the concrete to you is responsible. So in theory, you should break down the bridge deck and redo it, and all the costs for that, the ready mix company do that. So in order to avoid that, what the ready mix company do, if you ask for 4,000, they're gonna design 4,300 or 4,400 concrete for you, 4,500.
Well, higher, okay.
Yes, yeah. Almost all the jobs I've been on were higher than what we called for, all the time, because it's too much risk to take.
Yeah.
You know?
That makes sense.
Yeah. And just a side note, I want to show you. the surveying as a surveying, it's very simple job, very, very easy to do. But the liability of surveying is huge. Sometimes I go on a job, it's a huge site, and you start seeing still dirt, but you have catch basins already poured, you have curb and gutter already poured, you have columns already poured. So how did they do that? The surveyor read the plans and did his coordinate system and then decided this is where it belongs. What happened when the job is completed if some of those locations are wrong? That's a big liability. Big liability. Okay? Like another good example, on a freeway project, a lot of those bridges are supported by one big column in the middle of the bridge, right?
Mm-hmm.
What do you think the contractors start doing? Clearing and grubbing and digging for footings. So the surveyor tells them this is where the column is, and he puts a stake there. The contractor goes ahead and do this. They put the column before they form the bridge, right?
Mm-hmm.
Way before.
Yeah.
What happens if the location of that column is wrong? Somebody is going to be in trouble. See, this is why I tell you we are in a high liability profession. You have to be very careful. Making mistakes could kill people, or making mistakes could cost millions of dollars. That's why we have to be careful as engineers and then take everything serious out there. All right. So that's enough for that. Like I said, that these two numbers should be different. And then if they are close, let's say 2340, 2550, you take the average of the two. If this is 2340 and this is 1500, this is bad. So you throw that out and just use the close one. All right. So this is the tested beam. Look at the left first. Look at where the crack started. See that? It starts at the bottom. Why? Because we said tension is at the bottom. So, and then it's going to grow as the load continues. Of course, you don't stop the test here. We didn't stop the test until this stage. Look what happened to the crack. The width grew, and then the concrete crushed. But this happened before that. Remember what we said in the lecture yesterday? We said the steel is going to yield before the concrete crushes. This is the crushing I'm talking about. The steel yielding is going to be here. It's starting to yield right there. See that? Maybe not at this stage, maybe a little bit after. And then as a result, it's sagging. It's starting to sag. That's the yielding. But this happens at the end, way at the end, the concrete crush. So that's the crushing. This shows you compression at the top, tension at the bottom. Does that make sense to you now? Look at that. The crack from here to there, what happened to it? It opened up. That means something is elongating it. Something is stretching it out. What is that? Tension or compression? That's tension. So this is the tension at the bottom, compression at the top. Between the two, there's an imaginary line here we call neutral axis. Above it is compression, below it is tension. And that's that C distance we were talking about. Remember the C? When we did the strain diagram, that's that C distance from the neutral axis to the top, and C and neutral axis to the bottom as well. All right? See, this is the beauty of the lab. You see what we cover in the lecture in the lab. And believe me, this is good. This is good presentation, although we're not there, but I'm still able to illustrate that for you. Any question on that? All right, so then this group here, look, you can tell they were 1, 2, 3, 4 guys. So they just wanted to take a picture with their broken beam, I guess, for memory. So look at that. So there's the brake. And then this is the machine that we put there, and then the gauge, and then this gauge measured how much the deflection of the beam is. Now, remember, this is the delta, okay? And I'll show you the graphs in a second. So this is the delta, how much is going down. Now, look at this beam here. Look at the failure. This is different than that, right? This is different. We intentionally did that. That's why we put different groups with different things so you can witness both failures. This is a bending failure. right? Because we have tension compression. Look where the crack started and go there. Look at that. The crack didn't start here. The crack is a horizontal crack. It started in the middle of the beam. And you will see when we get to chapter 8, we're going to talk about that. This is a shear failure, we call it. You know why? Because this beam doesn't have stirrups in it. This beam, let me go back. This beam doesn't have these in it. Doesn't have this. One group doesn't just have 4 bars, and we just put one stirrup at the beginning, one at the end, just to hold it. But we didn't put any of this in. Why? Because we wanted the beam to fail in shear. And what is shear? Look at my hands. Shear is this. Shear is this. Okay? Bending is that. This is bending. Shear is this. And we said that one way to illustrate shear, we say the bolt on my tires were sheared off, meaning broke like this, sheared off. That's shear. So the mode of failure for shear, we'll talk about that in chapter 8. It looks exactly like this guy right there. So this group said the mode of failure for my beam was shear failure, due to the fact that no shear stirrups were used, of course. And I remember when this beam failed. This is a great picture, by the way. When this beam hardly took any load. You know, maybe 2 minutes into the test, this beam failed. Where this one took a long time to fail, because we have resistance for shear, we have resistance for moment, so it lasted a long time, where this one just failed. See? This is very dangerous in real life. We need to put shear reinforcement so this doesn't happen. All right, that's that. And then this again was measuring the deflection of the beam. All right, then what we did is we plotted the force versus deflection. Let me move this up. So this is testing of beams and cylinders. So this is delta versus force. The delta values is what we read on the red gauge. Remember that red device? So those are the deltas, and you'll see the numbers in a second. And then what about the force? How did we get the force? Remember, the machine gave us a pressure, PSI, but the manufacturer of the machine said in order to convert that pressure to a force, because remember, pressure equal force over area, right? Pressure equal force over area. So force equal pressure times area. So the manufacturer said, take the pressure you read and multiply it by pi, 3.14. So the 3.14 is equivalent to the contact area between the device and the beam. And you will see it in a little bit in there. Remember, guys, you have this presentation. So you have all that for you to use, use it in your report. You're free to do that. No problem. All right. And then, like I mentioned, this is mine, so I can share that with you. But the copyrighted ones, unfortunately, I cannot. So there you go. Move this back. So here you go. Hydraulic press, yellow in color. Remember, we saw that press machine. What happened to my picture here? Okay, sorry. I don't want you to go to sleep. All right. So the yellow machine is the hydraulic press. Delivers pressure in PSI. I mentioned that. The attached device, red in color, that's that deflection gauge, measures deflection delta in inches. How are we going to get the force? This force on the graph. Force equal measured pressure in PSI times pi equal 3.1415. Force equal pressure times area. See how much we're using this formula, guys? This comes from the deformable body class or strength of material. As simple as this formula, it gets used all the time. Okay, it says using pi for area is part of the testing device setup. The manufacturer told us that. So as the students, remember I said one student was pumping, another student was reading the pressure. another one was reading the deflection, and then another student was, as the deflection is read, they had a computer ready. He or she entered it into an Excel sheet with a formula already that would convert the pressure into a force. Very easy, of course, and that's how they did that. Or you can just write them down and then you do it later, either, no problem. But this is the force deflection curve of the beam. Okay. This is actual data from one of the tests we did. So for your lab, I'm going to provide this for you. I'm going to provide maybe the delta and then the pressure as if you read, and then maybe ask you to calculate the force and then plot the graphs. Okay, so we'll do that. And look how many points we have. Delta, pressure, delta, pressure, delta, pressure. Continuing. This is the test ongoing. Delta pressure until the beam broke. So the beam broke at a deflection of 0.328 inches, and the pressure, maximum pressure, was 6,400 psi. See that? Starting from there to there. So this is a good test data that we did in the lab. One of my labs, we did that. And then after that, what will happen? We're going to do the post-test calculation. We already talked about that. Same calculation you did in pre-test, but now you're going to use F prime C 4000 instead of, 2340 in this case instead of 4000. Okay? And then of course, so that's what this says. So you do that. And then again, it's shown to you in the presentation I showed you before for the lab. You also have that. So there you go. The F prime C was estimated at 4,000. We measured 2340. FY60, I don't know why we say 66,000, because we did not measure the steel in the lab, unless if the company, when we got our steel from them, they told us the FY is 66,000, but it's not important. So either way, it's fine. And then this FYT is the yield stress for the stirrups. It's 59,000. So no big deal, just use the numbers. And then here, this is what I'm gonna assign group 1, group 2, group 3. I'm gonna give you some numbers similar to those. So this is what you would have got in the lab if you tested your cylinders. See that? So the best, and I changed some of these numbers just to kind of make them different. But I remember nobody got anything above 3,000. So you will get these from me. Okay, this is like Thursday class, Friday class, Saturday class, something like that. So we're gonna redo the calculation for your group based on these F prime C's, which is easy. You already done that. Then here you go. This is the post calculation. And then again here, they're shown here also. Sorry about that. And they're shown also in the other presentation. So everything is the same. The only thing, look, F prime C is 2340. So follow that, and then you will get your value P from there. See, P equal 9.06. Okay, based on the post calculation. The pre-calculation, I think this was 10.9 or something. So of course this is going to be less because the concrete is weaker. So please, this needs to be in your report, okay? But everything is done for you. Everything is done. All you have to do is change your F prime C, the one I give you, then you do your calculation. All right, and then then here we're doing the shear, but we haven't done that yet until we cover chapter 8. But you will see it's very easy. We'll come back to that. And then see here, and this is the post-test calculation. So remember we calculated P for pre-test. That's the force we anticipated taken to break the beam. So based on moment, we calculated it's gonna take 9.06. And then based on shear, which we haven't done yet, it was gonna take 6.4, but we will do that. Okay. So this is the post-test. I remember, I think the pre-test, this was 9 point something. Okay, I don't want to look at it. Maybe it's in the next slide. Yeah, it's in here. See here, conclusion. Calculated beam was supposed to have a ductile failure, moment failure, 10.9 kips. See, this is the P we would have need to break the beam using 4,000 PSI. How much did we end up with? 9.06. See that? From 10.9, almost 11 to 9 because of the difference in strength. All right? And then the shear failure, I said we skipped that. Actual beam had a brittle shear failure. Actual design had a very weak concrete, 2340 versus 4,000. See that? And then using measured values found that our beam would have a brittle failure due to weak concrete, moment 9.06, okay, versus 10.9. And then the shear failure is 6.4. So based on that, what do you think the beam was going to fail at 6.4 or 9.06? It's going to fail here because this force is going to be delivered before that. So the beam would fail in shear before we even see that. And that was that beam I showed you where shear failure was happening. So that's that one. Okay? But your group could be different based on the F prime C, and then you can calculate those numbers, and then you can make your own conclusion. So everybody will have a different conclusion there. Okay, and that's it for that. Any question, guys? Again, please, to stay on top of things, stay with me, okay? Between now and next week, make sure you review all that. As a group, do everything you can, put it in a 3-ring binder. The only thing we're missing now is the shear calculations. And I don't want to just fake it. And no, I want you to understand the theory, and then we come back and do that. Very easy after that. All right? And then this is it. This is the lab. This is the end of the lab right here. Okay? So what I'm going to work on is giving you those data numbers, and then the F prime C and all that. And then we will come back to this at the end when we do the, not at the end, chapter 8, when we do the shear calculations. So again, next week, we're going to do the beam design, slab design. Then we'll turn back onto the project so you can do your beams and slab designs. And then from there, we'll go to the wood column design, and then you do your columns. So we're doing very well time-wise, okay, considering the circumstances. But stay with me, okay, week by week. You're gonna feel much better. You understand the stuff, and then you're not gonna feel overloaded at the end of the semester. All right. Any questions, guys? Any questions? All right. If not, then I'm gonna take a roll call if you don't mind.
Professor, I have questions on
yes.
I have questions on the project.
Sure.
Go ahead. So for our project, my group did most of the calculations already for like the beam, the TV beam, and everything.
Good. Okay.
I had just a question. So when we calculated the slab weight, and
yes.
For our group we got L2 to be 30 feet, so we got the same numbers as you did in yours.
Okay.
That 119 total dead load pounds per square foot. That's the dead load of the slab. Am I correct?
Yes, absolutely.
Okay. So, do we ever, once we calculated the dimensions for the beam, and then we use the 119, that's the dead load of the slab on top of the beam. Am I correct?
Yes, that's the weight of the slab going onto the beam.
Okay, on top of the beam. Do we ever consider the self weight of the beam itself?
Yes, very good question. You're good, really. Thank you for that. Yes, and we will do it at the end, toward the end. That's why what we're doing now, we call it preliminary design. See that?
Uh-huh.
We are doing preliminary design.
Okay.
Now, once we design the slab with the rebars and the beams with the rebars, we will go back to that and fine-tune that. But absolutely, Remember when we illustrated the DT beam
Yeah.
and we picked that square that we wanted the program to calculate the own weight of the beam?
Mm-hmm.
Yes, absolutely, we're gonna do that. But now when we do the beam design, we're gonna learn how to calculate the own weight of the beam.
Okay.
So once we get that, and toward the end, we'll go back and refine our design, and then we will consider all that. Good
I see.
question, very good question, really.
So for now, we'll just disregard it when we do our weight PU for the
Yes.
column.
Yes,
Got it.
just do it as we did in the class, and later on we're gonna refine that, and it will be very easy to refine for you.
Got it. That makes sense.
All right?
Thank
At
you.
least you understand the process now.
Mhm.
So numbers could change a little bit, no big deal, but you understand the process. That's why even in real life, first round we call it preliminary design, because we know it's gonna change. But like for now, we assume the beam dimension, this and that and all that. What happened later on when I pick my steel and I find myself the epsilon T is within the transition zone? I'm gonna change my beam. So that's why we don't do that till the end. So very good question though. Thank you.
Okay.
Any other question?
One more question.
Yes.
Would you mind going to your PowerPoint presentation?
Sure. 1 second. Okay. You can still see it, right?
Right now, we can see only the post-testing calculations for the lab you were just covering.
All right. Very good. Let's see. So you want to go to my chapter PowerPoint?
Yeah. So the PowerPoint for the project.
Oh, for the project.
Yeah.
Okay, no problem. Let me do that. So let me project report. Okay. Just give me a second, please. Project. Class project. Okay. Okay, I'm there. Let me share my screen.
Thank you.
You're welcome. Okay, can you
Okay.
see it?
Yes, Professor. If you go,
Class project. Okay.
if you
So,
go, if you go down to the beam slab calculations. So
okay,
keep
very
going.
good. Let's do that. These
Okay.
ones?
Okay, yeah. So that's where we get. So I understand that. Go to the next slide.
Okay.
Okay, this one is where we get the weight of the slab, the dead load and the live load of the slab onto the beam. But what is the one after that one?
This one?
Yes.
Okay. This one is we are getting the weight of the slab, how should I say this? Okay, this is the slab itself. This is the slab itself sitting on the supports, right? So this is the slab itself. There's the live load and there's the dead load of the slab. So we get the loads of that. From this slab, we go ahead and take the loads to the beams.
So
You know what I'm saying?
So that WU from that other slide would be added to this WU?
Later on, you mean?
When we start calculating the full load on the beam.
Okay, let me see. So this WU is what the slab is, and then this is the actually no. This WU in the slab is already here, is already in the beam. See that? Because remember we did the same one, 119.
Yeah.
So it's already here. The only reason is we need it here. I need to put it on the slab so I can design. I can later on design the steel for the slab. How much rebars I need. Does that make sense?
Okay. No, not really.
So just do it like this, and later on when we do the final design, it's gonna all work together. Don't worry about that.
Okay, so basically we're not using this right now, are we? Like when we're putting in our final load on DT beam, we're not using this right now. We're only using the other calculations, correct? The top one from the other slide.
Yeah.
Okay.
But when you do the DT beam for the slab, you're gonna use this.
When we do it for the slab, because right now the DT beam that you showed us, that's for the beam. Am I correct?
No, this one is for the slab.
Yeah.
Yeah, I think the example we did is for the beam, right?
Yeah.
Yeah, but you're gonna do the same thing using these numbers for the slab. Okay, because why? Because the moment that the DT beam is gonna give us from this setup, we're gonna calculate the steel we need in the slab. And then when we did the DT beam for this, it's gonna give me, remember, moment and shear diagrams. I'm gonna use those moments to select the rebars for this beam. Make sense?
A little bit, yeah. Okay.
Okay. Yeah, but that's really it. So think about this. The slab is carrying this load that we calculated here. So I can find the moments in the slab, and that's the slab, meaning the area between the beams. I need to pick up rebars for that. So I need to do this. And then ultimately these beams is carrying 7.5 feet of the slab on each side.
Yeah, I understand this one's, yeah.
Yeah, and then that one, that is there. Yeah, okay. If you understand this, then believe me, it's the same there.
Okay, because, so we just hold on tight on this one.
Yeah, hold on tight.
Got
okay,
it.
Let me explain it another way.
Okay.
You understand how the load is going from the slabs to the beam. No
Correct.
Problem, right?
No problem.
Okay, now look at the slab here. This slab, before the force is gonna get to the beam to carry it. This. Before the force load is gonna get to the beam. Here we're assuming that the load is getting to the beam, and we're gonna design that.
Okay.
But before the load gets to the beam, the load is here between the supports. So the slab has to carry that. Does that make sense?
Oh.
So I have to know these loads, and then what kind of rebars I'm gonna put between these supports to get there.
Oh.
Okay, so that's the idea of that.
I see. Wow. Okay.
Yeah, good questions though, very good. But trust me, it's gonna all be clear at the end. Don't worry.
All right. Thank you, Professor.
All right, you're welcome. Good job. Good questions though.
I do have a question, Professor.
Sure.
Yeah, this is actually not about this lab, but it's about the last lab, right? For the last lab that we did, right, was if I'm correct, that file was named, I think, it had like the stirrup photo onto it, right? The profile of Professor Terzig's form.
Yes.
Okay, so that one, right? So we fill that out, and the values that we get on there.
You may just switch back. Let me switch back to that presentation. 1 second. Let me switch back to the lab. Class. There you go. Can you see in my lab now?
Yes, sir. I can see it.
Okay, let's go back to the beginning.
Because now, of course, we did that one last week. Then we have to do this one where you're going to give us the values this week, right?
Yes. Yeah, I'm going to give you the values this week so that as if you're this is what you get out of the lab. So this is what you were talking about, Dr. Terzig?
Okay, so yeah, that one right there. Yeah, so those ones, right?
Yeah.
Okay, so that one's we have to do, right? So we have just that one and this week.
You should have already done that.
Well, no, I just want to confirm. So this one.
Yeah, I know. No problem. Yeah, this is like we said. You would do this. 1 second. This one, based on F prime C 4000.
Yes.
And you're gonna find the number of bars you need, and what is the value of P you need. And we said skip the shear here until later, right?
Yeah.
So that's the one. And now we're gonna do the post test when we determine F prime C is not 4,000. And that one is shown in the, and anything on these pages before I flip?
Not at the moment, sir.
Okay. So see, remember, these are the pre-test calculations.
Yeah.
We did that, F prime C 4,000. And then you did all that, and then we discussed all this. So let's go back. Let's go forward. When we find F prime C, then we're gonna do the post. And I'm gonna give you these results. You're gonna do the post-test calculations, which is here. See, post. And then the F prime C is 2340. So you will do that. So you need from me as a group, what is this F prime C value? Okay, so I will definitely do that for you within the week, next week, or this weekend if I'll try. Is there any question? Any other question? Any other question from anybody? All right. If not, we're done, but let me take attendance, please, quickly. Let me see if I know what happened to it now. Okay, let's see. Okay, I'm gonna call names here. Let's say Adis. Adis, are you there? Okay. Let's see, Park.
Here.
Minmo Park, you there?
Yes, here.
Okay, Alexis.
I'm here.
Okay, Arba.
Here.
Okay, Binyam. Binyam.
I'm here.
Okay, Biri. Biri.
Here.
Okay. Sorry if I mispronounced somebody's name. Carlos.
Here.
Griffin. Brown.
Here.
Okay. Let's see. Joycelyn.
Here.
Okay, thank you. Let's see. Myra.
Here.
Nick.
Here.
Paulo.
Here, Professor.
Okay. Let's see. Raymond. Lamb.
Here. Listen.
Sean. Lowe.
Here.
Okay. Anybody I didn't call?
Watch the show.
Huh?
Did you see?
Okay, thank you. I got that. Who else? Anybody else? Okay, I think we have full attendance except Adis. Is Adis there?
Yeah, he's here. I don't think his mic is working.
Is that okay? All right, that's fine. We have full attendance then. Okay, thank you everyone, and then I will have a nice weekend, and I'll see you next week then.
Thank you, Professor.
You're welcome. Thank you.
Thank you.
You're welcome.
Professor, I have a question for you. Aside
Yes.
from all of this, I was just
Sure.
wondering. Do you ever like at all? Cause I like most of the professors in school, like they're either like they don't work in the field anymore. So like
Yeah.
I was wondering if you ever have like a shadowing of students to check out like the working sites that you go to. Like, do you ever do anything like that?
I am very, I would love to do that.
Like,
I'm
just to
very
see,
busy
you know?
person, as you can see.
Yeah.
But I will see if any opportunity jumps. I will let you guys know. Maybe we can do a field trip or something.
Yeah, that would be really cool, Professor.
But I am very, very, very busy. You
Yeah.
won't believe how busy I am. But I will keep that in mind, and I
Thank you.
appreciate the request.
All right.
If I do have an opportunity, I will let you guys know.
Okay. Thank you, Professor. Appreciate it.
You're welcome. You're welcome. Anytime. Have a nice weekend, everyone.
You do too. Bye.